Hello students, today we will talk about conservation theorem for total energy of the system of n particles. T- Total energy, it is the sum of kinetic energy and potential energy. Kinetic energy we are going to represent it by capital T, and potential energy we are going to represent it by capital V. The total energy of a system will remain constant only for many particle system. There are two conditions. One is if the external force applied on the system is conservative force. If the external force is conservative force, then maybe the total energy of the system remains constant. Second, the internal forces, that is the forces due to in between the particles, that is interaction in between the particles, the mutual interaction in between the particles, if these forces are central forces or they just exist in pair, if ith particle is applying force on jth and jth particle is also applying force on the ith particle, then these internal forces are central forces or maybe conservative forces only at these two conditions. uh, When the external forces conservative in nature, another the internal forces are central forces, only at that condition the total energy of the system remains constant. Now we will discuss how these two energies, kinetic energy and potential energies, are going to contribute in the total energy, and how these two energies make the total energy constant at these two conditions: external forces conservative force and the internal forces are central forces. Let us consider that we have a large number of particles in the system, and this is our first particle having position vector r1 with mass m1, velocity v1. And similarly, let us consider this is our second particle. Again, this is our r2 position vector with respect to the origin O and coordinate axes x and y. Similarly, let us consider this is any particle, ith particle, and having mass mi, velocity vi, and the position vector is ri. Similarly, consider any particle. Let us consider this is our jth particle having mass mj, velocity vj, and the position vector rj. Similarly, this is our last point or particle in the system, and let us consider it is indicated by it is indicated by n, and the mass is mn, the velocity is vn, and the position vector of this particle is rm. This is our whole consideration. Now if we consider only on the work done on the particle, it depends upon the force. And if there are two type of forces on each particle, then it means there are two type of work done the particle will have. Uh, Let us consider this is our ith particle, and this ith particle, as we have already represented with position vector ri, mass mi, and velocity vi, experiences an external force. If it is experiencing an external force, this external force, any push or pull from the outsource, is represented by fie. And we know very well this ith particle are attracted by another particles, or this ith particle is also attracting other particles. Let us consider the jth particle. Again, the position vector is rj, the mass is mj, the velocity is vj. We know that is a displacement vector in between them, and this displacement vector, which can be represented by from RJI, can be given with the help of right angle triangle of vector addition. That is, these two vectors are in anti-clockwise direction, then this vector is going to be in clockwise direction, give their resultant. It means Ri is equal to Rji plus Rj or we can say that Rji can be given as Rj minus Ri. This is this is the displacement vector. This is the distance in between these two particles, that is J particle and I particle. Now in this regard, we know that ith particle is applying a force on jth particle and jth particle is applying a force on the ith particle. Now we are representing it by Fgi. It means the jth particle is applying a force on the ith particle, and force is a vector quantity, so we are applying an arrow on this vector and it is represented by Fgi. What is the direction of Fgi? Fgi, jth particle is applying a force on the ith particle. It means this is the direction of Fgi. Because jth particle is applying the force on ith particle, jth particle is attracting the ith particle in its direction, and this is the direction towards the jth particle. It means what is the relation between Rgi and Rgi? They are opposite in direction. So we can represent this Rgi in the direction of Fgi can be represented as Rij. That is the displacement vector relation with your internal force. Hence, the total force on the ith particle can be given as, that is Fi, the force on the ith particle, is given as the external force on the ith particle and the internal force on the ith particle. But only jth particle is not applying force on the ith particle. First particle is also applying force on jth ith particle. Second particle is also applying force on the jth particle. Similarly, third particle is also applying the force on the ith particle. So we have to find the total forces on the ith particle. So we will make the summation from 1 to n, where condition is that I is not equal to j, because for I equal to j, this will come out 1 1 f11. It means first particle is applying force on first particle, and this is not possible. Now we have to do some work. If we have to do some work, if we are applying these forces and this particle gets shifted a little bit, let us consider from Ri it shifted to this position, and this position is Ri plus dri, where dri, that is a small shift in the position vector of I. Similarly, if we apply the force on the whole system, it means jth particle will also shift, first particle will also shift, and so on, all the particles will shift. So what will be the work done on the ith particle? On the ith particle, the work done can be given as Fi dot with dri, that is a small displacement, and this is equal to, if we are multiplying with dri in the left hand side, we have to proceed the same in the right hand side. We get summation Fie dot dri plus summation Fgi. As we are moving the ith particle, we are taking dot with dri, and the summation goes from j to 1 to n, where j is not equal to I. We are not talking about the small work done. We want to shift the whole system from position 1 to 2. If the whole system is shifting from position 1 to 2, it means ith particle is also shifting from position 1 to 2, that is the initial position, to the final position. To find the total work done, we have to shift the particle from position 1 to 2. So we are just taking in or integrating from the initial position to the final position. This is representing the work done on the ith particle, because still we are just dealing with the ith particle, but the whole system is moving from position 1 to 2, not only the ith particle. For the whole system, we have to add the work done for the first particle, second particle, and so on. So we have to make summation for all the terms, and here the summation is for I, and the I summation moves from 1 to n. Similarly here we will put 1 to n. Similarly here we will put 1 to n. Here the summation is of for the j. Here we are taking the summation for the j, but here we are taking the summation for the I. And now if we for this particular term there are two summation. One is from I is equal to 1 to n, and for one another is from j is equal to 1 to n. Now we will talk step by step for the kinetic energy and work relation. Let us consider this is the we know that the total force on the ith particle is denoted by Fi, which we already shown here. This is the total force on the ith particle, and we know that the displacement shown by the ith particle is Tri, so we can find out the work done on the ith particle, and this is the total work done, and total work done can be represented by Fi dot Dri, that is the ith particle work done from 1 to 2, but there are large number of particles, so we have to give a summation to all the particles so that we can obtain the total work done. Just use the Newton's second law of motion, according to which F is equal to dp upon dt. Then if we just put all these condition, we get d. Instead of Fi we will have dpi upon dt dot with dr. Just put the value of pi in the terms of mass and velocity, we will get that is mi vi will be the vector, mi is a scalar quantity, dot with dri. If we just take these two terms, dri upon dt, this is nothing, it is the displacement of the ith particle with respect to time. It means it is representing the velocity of the ith particle. So we can take this mi, it is a constant, so the change will be with velocity, the velocity will change, and dri upon dt, that is nothing, it is the velocity for the ith particle, and the ith particle is moving from the initial position to the final, and this is representing the total work done by the system, as we have taken the summation for all the particles. Just undergo summation for these two terms. Here summation is of velocity, just increase the power of velocity by 1 and divide by the total power. You will have half of mi vi square, and the limits are from 1 to 2, and the summation is from I is equal to 1 to n. This is the total work done. If we put substitute 2 here, it means we are talking about the final kinetic energy. If we are putting these limits, we are talking about the initial kinetic energy. It means we are talking about the final kinetic energy of the ith particle, and the total kinetic energy, initial kinetic energy of the ith particle, that is with a subscript of 1. Just this is indicating that this is the final kinetic energy of the ith particle, this is the initial kinetic energy of the ith particle. If we are just taking the summation, it means we are taking the total energy for the whole system. It means it is representing the total kinetic energy of the whole system at final point, and this is indicating the initial total kinetic energy for the whole system, and this is the relation in between the work done and the kinetic energy. It means work done is nothing, it is the difference in the final kinetic energy and initial kinetic energy. If we take the difference of the kinetic energy at initial position and final position, it will nothing, it is representing the work done. Let us consider this is our equation number 1. Similarly, we will find out the relation in between work done and the potential energy. But as we have two type of forces, one is external force and another is internal force, and both forces are conservative. All the central all conservative forces are central, and as our internal forces are central forces, they may be conservative forces, and the applied external force is conservative. It means we can just indicate it with the help of a potential. Just we are going to discuss what happens, what is the relation in between potential energy and the work done. Again we are taking that on applying some force, we are moving the whole system from position 1 to position 2, and on ith particle the total force is given by the internal force and the external force, and the particle is displaced with the displacement of dri. If we take summation for the ith particle, we will get for the whole system, and for limits we have to move the particle with a displacement from 1 to 2. This is the whole setup. Just first we will discuss about this term. What is the contribution of this term? If we take for the external forces, we will get fi, external force on the ith particle, and change in the position of the ith particle from 1 to 2. And if we get summation, we are just talking about the work done by the total external force on the whole system. As this force is conservative in nature, so we can give this force as the change in the potential energy. If external force is conservative in nature, then and only then we can represent it with minus gradient of vi, that is the potential energy of vi, that is the ith particle. And this is nothing, it is the change, maximum change of potential energy, where the force is showing the decrease. The negative sign shows that the direction in which the uh, potential energy is decreasing, in the opposite direction the force is increasing. And this quantity, it is nothing, it is the change in the potential energy with respect to the displacement, and displacement in our case is dri. So we can put this whole thing here. This can be written as, this also known as gradient of vi. So we can put force, conservative force as gradient of vi. We will get summation and integration, both should be taken, minus gradient of vi and dot with dri. And this is nothing, it is again we will just putting the value of this gradient. We will get 1 to 2 summation, and with the negative sign, we are taking just negative sign outward just before the summation, and we get here dvi dri dot with dri, just cancel out these two terms, and on integration of dvi, what will you get? You will get vi, that is the potential energy for the ith particle. And this potential energy of the ith particle can be at initial point 1 and final point 2. We can put the limits, and just we are putting the summation. A summation goes from 1 to n with negative sign. Let us consider this is our equation number 2. This equation number 2 represents the change in the potential energy of the ith particle will give the work done when the applied force is conservative in nature. This negative sign indicates that the potential energy decreases as we move from initial position 1 to initial position 2. Similarly, we will find out the relation of potential energy and work done for internal force case. As we have substituted Fi, the external force, in the form of gradient of the potential energy of the ith particle, similarly, we can just represent the internal energy on the ijth particle due to the ith particle, because this internal energy is also conservative force. This force is also conservative force, then we can represent it as a del operator of Vij, that is the potential energy of on the jth particle due to the ith particle. Then what will be this, how can we represent this? uh, should we take here Ri, or should we take here Rj? What we will consider here, because as we are discussing the force on the jth particle, so we are taking the change in the position for the jth particle, and hence we are putting here delta j. Similarly, when we talk about fji, we are taking the internal force on the ith particle. It means jth particle is applying force on the ith particle. It means the position of the ith particle will change now. So we are taking the del operator change of potential energy with ith particle, and we are representing it with vgi. Again, just consider, you have ith particle, you have jth particle, and this is your position vector for ith particle, that is Ri. This is the position vector for the jth particle, Rj, and ith particle is applying the force on the jth particle. It means the ith particle will move the jth particle in this direction, and this force is given by ith particle is applying the force on the jth particle. It means the position of the jth particle will change. Similarly, jth particle will apply force on the ith particle. The force will be, jth particle will attract the ith particle towards itself. It means it can be represented by Fji. Then whose position will change? The force is experienced by a ith particle. It means the position of the ith particle will change now. Now, what is the change of Ri with Rj? These particles are independent of each other. Ri is not depending upon Rj. It means change of Ri with change of Rj is equal to 0. Similarly, the position of Rj is not changing with Ri. These particles are independent of each other. It means we can't say that the position of the jth particle is depending upon the position of the ith particle. Again, this term is equal to 0. Now, just moving towards our mathematical part, what is Vij is representing? Vij is representing the potential energy in between these two particles. The potential energy between these two particles is represented by Vij, or it can be represented by Vgi, because potential energy, it is a scalar quantity, it does not indicate direction, and potential energy depends upon the position of these two particles. The separation in between two particles, that is J and I particle, can be represented by R vector minus Rj vector with magnitude. We have to show only the distance in between them. The direction is meaningless in case of potential energy. So whether you are taking the distance from I to J or from J to I, the distance is same. So we are taking the potential energy on ith particle due to jth or jth particle due to ith. They are one and the same, and we can substitute this. And this, both these potential energy, they depend upon the distance in between the two particle, and distance in between the two particles given as Ri minus Rj magnitude, because we are not considering their direction. this is not in multiplication, we are only showing that this potential energy is a function of this. For example, we show the function like that f is depending upon x. Here we are only showing that v is depending upon the distance in between these two potential energies are same in magnitude. So, what is Fij? Fij can be written as, this is the force on the jth particle. So we have to take the del operator of the jth particle, because the position of the jth particle will change. Jth particle is experiencing the force, and we can represent it the potential energy in between the I and jth particle. This can be represented as change in the position vector of Rj, and it will change the potential energy. We can just represent it like this. It can be represented like this. Uh, Taking instead of Rj, we can take the distance in between the ith and jth particle. Just multiplying and dividing by the same thing, it will not changing going to change our uh, term. We are getting the same results, and this term is representing nothing. It is representing the distance in between the ith particle and jth particle, and we are taking these two terms, and this term is representing the distance or displacement vector in between these two particles. So we are taking these two terms together, and now we are left with minus and with change in the displacement vector in between the particle I and j, and we have this. And according to our assumptions, ith particle position is independent of jth particle. Already we have put it that this is term is equal to 0, so we can see that this first term is equal to 0. Jth particle is changing with jth particle, the derivative comes out to be 1, and here we have change with respect to the position in between the ith particle and jth particle, and we will get that is change with respect to distance in between ith particle and jth particle. Negative negative becomes positive here, and this is our Fij, and can be written in the form of del ij Vij, and this is Fij, that is the force on the jth particle due to the ith particle. Similarly, we can find out Fji, and Fji comes out to be Fji. Similarly, we can find out Fji comes out to be with the negative sign Fij Vji, where Vij and Vji are same. Here we will have a small difference in these two. Here we get Ri divided by Ri, so this term comes out to be negative. In our this expression, we will get 1 minus 0 instead of 0 minus 1. So further moving to our towards our conclusion, what we are going to have, we have to find out the work done for the internal forces, and this is our internal force on the jth particle due to the ith particle. So we can represent it with the help of this, and we are moving the particle from position 1 to 2, and we are not moving single particle, we are moving all the particles, and this can be represented as the uh, summation of the forces Fij and Fji. As both forces are taken, it means we are just doubling the forces, so we are just making them half. We are putting Fji dot with Sj plus this is F and Si, because we are now representing the force on the ith particle. So this is I, and this is F Ij. Now we are representing the force on the jth particle, so the position of the jth particle will change. We are just doubling these terms, so we are making this half so that our left hand side and right hand side becomes equal. And from our above conclusion, we are putting all these forces in the form of their gradient. We already discussed about these terms. We These forces are conservative, so we are putting them in the form of their potential energy, and we get, for the first term, that is FGI, we get minus delta Ij do Vij and dot with DSG. Similarly, for the second term, we will get del Ij Vij dot with DSG. This will be GI, this will be JI, so this will be DSI. Now we are just taking common because we know that Vij and Vji both are equal. They are not giving anything new to us, so we are putting, and del ij and del ji, both are representing the same terms. So we are taking del ij Vij dot with dsj plus del ij, just we are putting this. Differentiate with respect to rij or rgi. Rij or rgi, they are representing the same distance, the distance in between the ith particle and the jth particle. So we are putting these two del's operator uh, as same, that is del ij, and now we are putting again this del ij. Vij and Vji both are representing the same scalar quantity. So the difference is that here we get dsg and here we get dsi. Just make common, take the common terms, and we will have d del ij Vij and taking dsi minus dsg. This will be our last result. We are just putting, uh, taking the common terms, and what this term is representing. This term is representing nothing. It is representing the um, distance in between the ith particle and jth particle when they got a displacement of dsi and dsg. So we can put this half of summation 1 by 2 del ij Vij, that is the displacement in the position of the ith particle and jth particle, which can be represented by drij. So what is this thing is indicating del ij Vij, it is representing nothing. It is representing the change in Vij when there is a change in the distance in between Rij. So we can just put this value here and cancel out, and you will get one, that is 1 by 2 summation, and 1 by from position 1 to 2, and we get dvij as we have cancelled out these two terms. And this term is indicating the change in the internal potential, and if we just integrate it, we will have minus 1 by 2, as we have just take the negative sign common from here. What will we get? We will get dsg minus dsi. If we take this sign common, we will get this negative term and this will get positive, and there is nothing change here. We will get the minus sign here, and if we integrate this, we will get the summation, and integrating this we will get Vij from 1 to 2 position. This whole term is indicating the change in the potential energy because of internal force. This is our third relation, and this term was indicating the change in the potential energy due to the external force. Potential energy due to the external force this is the potential energy due to the internal force. Then what is the work done by the total potential energy? It is given as, because both these have negative sign with them and a summation, here is also we have a negative sign and summation. We can take negative sign outside using equation number 2 and 3. We get summation of Vi, that is the potential energy due to the external forces, plus half of summation of Vij, this is the potential energy due to the internal forces when the particles are moving from position 1 to 2. So if you are adding potential energy to potential energy, you will get a potential energy. Let us consider that total potential energy comes out to be V, and if this is the final potential energy, this is representing the initial potential energy, we will have minus V2 plus V1, or we can say that V1 minus V2. It means in case of work done, how potential energy is related with work done. Potential energy is moving a system from point 1 to 2 can be given as the initial potential energy minus potential final potential energy. And in case of kinetic energy, we find out that this is the relation, that is the final kinetic energy minus initial. Both quantities, both equations are representing the same work done. It means V1 minus V2 is nothing, it is T2 minus T1. If we just uh, take the initial terms at one side and final terms at another side, you will get sum of initial kinetic energy and potential energy is equal to the sum of final kinetic energy and potential energy. It means the energy is constant, and hence we proved our relation that for external forces conservative and internal forces central, the total force remains constant. This is all about the law of conservation of energy for many particle system. The condition is that internal forces should be central forces and external forces should be conservative forces, so they can be changed put into the scalar potential function.